In the extraordinary universe of wartime experimental weapons, where desperation and ingenuity combine to produce ideas that range from the brilliantly practical to the magnificently absurd, there exists a concept so fundamentally audacious that it challenges the imagination even decades later. It was an idea that seemed to violate the basic logic of two entirely different types of warfare simultaneously, that took the heaviest and most earthbound weapon of the land battle and attempted to give it the freedom of the sky. It was the flying tank, and in the desperate years of the Second World War, British engineers, military planners and aeronautical designers pursued this seemingly impossible dream with genuine seriousness and considerable technical effort. The concept asked a simple question, whose answer proved enormously complicated. What if a tank, the armoured behemoth that dominated the land battle but was imprisoned by roads, bridges, and the tyranny of logistics, could simply fly over all these obstacles and descend directly onto the battlefield wherever it was needed? What if armoured forces could appear from the air, bypassing every defensive line and every geographic barrier, landing behind enemy positions and striking before any response could be organised? The implications for warfare were staggering, the engineering challenges were immense, and the solutions that British designers attempted were among the most creative and most hazardous experiments in the history of military technology. Among these attempts, the Baines Bat glider stands as perhaps the most technically sophisticated and seriously pursued, a one-third scale flying testbed for an idea that might have transformed airborne warfare had the engineering challenges been surmountable and the strategic context remained favourable. This is the story of Britain's flying tank experiments, of the engineers who dared to imagine tanks with wings, of the tests that proved some things possible and others catastrophically dangerous, and of the reasons why this most audacious of wartime concepts ultimately gave way to the more practical but less romantic solutions that actually won the war. The fundamental strategic problem that drove interest in flying tanks was one that military planners had confronted since the earliest days of armoured warfare: how to get tanks where they were needed quickly enough to exploit opportunities that might last only hours. The tank's great virtue was its combination of firepower, protection, and mobility on the battlefield itself. But getting tanks to the battlefield was an entirely different matter. Tanks were heavy, mechanically demanding, fuel-hungry vehicles that required roads, or at least firm ground capable of bearing their weight. They needed to be transported by rail or ship for long distances, a process that took days and was highly visible to enemy intelligence. They could be damaged or broken down during transit. They could be delayed by destroyed bridges, flooded rivers, and terrain that became impassable in wet weather. Against a mobile enemy who could strike and withdraw before conventional armoured forces could respond, the tank's battlefield mobility was irrelevant if it could not get to the battlefield in time. Airborne operations had demonstrated that troops could be delivered behind enemy lines by parachute and glider, bypassing geographic and defensive barriers that would have stopped a ground advance. The airborne soldiers of the Second World War, Britain's Parachute Regiment and Glider Pilot Regiment, America's airborne divisions and Germany's Fallschirmjäger, had shown that determined men delivered from the air could seize objectives far behind the front line, hold them against initial counterattacks, and create strategic disruptions disproportionate to their numbers. But these airborne soldiers had a critical weakness. They were infantry, lightly equipped and almost entirely without armour or heavy weapons. They could be dropped behind enemy lines, but they could not bring tanks with them. When they encountered enemy armour, as they inevitably did in major operations, they were desperately vulnerable. The catastrophe at Arnhem in September 1944, where British airborne forces holding the bridge found themselves fighting German SS Panzer units with little more than infantry weapons and a handful of anti-tank guns, demonstrated with brutal clarity what happened when airborne troops faced armour without armoured support of their own. The solution seemed obvious in principle: develop a way to deliver tanks by air. If tanks could be air transported and landed near their objectives, they would provide the airborne forces with the armoured capability that gave conventional ground forces their decisive power. Combined with infantry, armour could hold ground against counterattack, break through defensive positions, and exploit success in ways that infantry alone could not. An airborne armoured force would be the ultimate expression of the Blitzkrieg principle. Concentrated shock applied at the decisive point before the enemy could respond, arriving not along predictable ground routes but from the air, from any direction, against any target regardless of its geographical isolation. Several approaches to air-delivering tanks were pursued during the war, and they reflected different assumptions about the scale of the problem and the technical means available to solve it. The most straightforward approach was simply to carry tanks inside large cargo aircraft or gliders, landing them at captured or constructed airstrips near the objective. This method was limited by the size and weight of tanks. Even the lightest practical combat tanks of the period weighed several tons, requiring aircraft of very large capacity that were difficult to land on improvised airstrips in contested areas. The Americans pursued this approach with some success using light tanks and tank destroyers in their Waco and Hamilcar gliders, but the vehicles that could actually be delivered were so light that they offered only marginal armoured capability against the medium and heavy tanks of the German panzer forces. A more radical approach envisioned attaching wings and control surfaces directly to a tank itself, transforming it temporarily into a glider that could be towed by a conventional aircraft and then released to glide to the battlefield. On landing, the wings would be jettisoned, and the tank would immediately be operational as a fighting vehicle, without the need to unload it from a separate transport glider. This was the concept of the flying tank in its most dramatic form, and it was pursued with genuine seriousness by engineers in Britain, Germany, the Soviet Union, and the United States during the war years. Each nation's experiments reflected its own technical capabilities and doctrinal priorities, but all were grappling with the same fundamental challenge: making something as inherently unsuited to flight as a tank actually capable of being airborne. The Soviet Union's contribution to flying tank development was perhaps the most ambitious, though its results were limited. The Soviet engineer Oleg Antonov, who would later become famous for his massive cargo aircraft designs, developed a concept he called the Antonov 40, which attached a biplane wing and tail assembly directly to a T-60 light tank. The theory was that the tank, fitted with its wings and control surfaces, could be towed to altitude by a bomber, released, and glided to a landing zone where the crew would detach the wings and drive away in their tank. A single test flight was conducted in 1942, with the tank glider being towed to altitude by a Tupolev TB-3 bomber. The results were instructive. The combination was so heavy that the towing aircraft struggled badly with the load, the gliding characteristics of the tank with its attached wings were poor, and after a single test glide, the project was abandoned as impractical with available power plants and materials. Britain's approach to the flying tank problem was more systematic and more carefully grounded in aeronautical engineering principles, reflecting the country's strong tradition of aircraft design and its experience with military glider development. Rather than attempting immediately to fly an actual combat tank, British designers recognised that the aerodynamic and structural challenges needed to be understood through scaled testing before full-size development could proceed. The approach also reflected a more specific strategic vision. Rather than attaching wings to an existing tank, British designers conceived of a large military glider specifically designed around the dimensions and weight of a particular tank, optimised to carry that specific vehicle and nothing else, with performance characteristics calculated to make the concept operationally viable. The tank selected as the subject for the British flying tank programme was the Tetrarch light tank, a vehicle that combined the lightest practical combat capability with a weight that was at least theoretically compatible with glider transportation. The Tetrarch weighed approximately 7.5 tons, armed with a 2-pounder gun and a machine gun, and provided modest armour protection adequate against small arms and shell fragments, though not against anti-tank weapons. It was not a powerful tank by the standards of 1943, but it was the lightest vehicle that could be considered a real fighting machine rather than a reconnaissance vehicle, and its weight was at least within the range that a very large glider might conceivably carry. The Hamilcar glider, Britain's largest military glider of the Second World War, was developed specifically to carry the Tetrarch and similar heavy loads. The Hamilcar was an enormous aircraft by glider standards, with a wingspan of over 110 feet and a fuselage large enough to accommodate a Tetrarch tank through nose doors that opened to allow the vehicle to drive directly out onto the landing zone. The Hamilcar could carry a payload of approximately 17,000 pounds, sufficient for a Tetrarch tank with its crew and some additional supplies. The glider was towed by 4-engine bombers, typically Halifax or Lancaster aircraft, which had the power to haul the heavy combination to operational altitude and deliver it to the release point. This was the more conservative approach to air-delivered armour, carrying the tank inside the glider rather than attempting to fly the tank itself, and it was ultimately the approach that saw actual operational service, But parallel to the Hamilcar development, a more radical experiment was being pursued that directly addressed the flying tank concept in its most ambitious form. This was the Baines Bat, officially designated the Baines Carrier Wing, a project conceived and designed by the aeronautical engineer Leslie Baines. Baines proposed that a full-size glider wing and tail unit could be attached to an existing tank, converting it directly into a glider that could be towed to the operational area and then landed under control before the wing and tail assembly were jettisoned. The concept was elegant in its simplicity. No specialized transport glider was needed, no separate aircraft to carry the tank, just the tank itself with temporary flight surfaces attached. On landing, the crew would detach the flying surfaces in a matter of minutes, and the tank would be immediately ready for combat. The engineering challenges of the Baines concept were formidable. A tank is, from an aerodynamic perspective, one of the worst possible shapes imaginable for an aircraft. It is heavy, dense, and designed entirely without reference to the principles of aerodynamic efficiency. Its center of gravity is typically low and forward, appropriate for a ground vehicle that needs stability against terrain obstacles, but deeply problematic for an aircraft that needs specific center of gravity relationships to the center of lift to achieve stable, controllable flight. The wings and tail surfaces attached to the tank would need to be designed not just to provide adequate lift for the tank's weight, but to position that lift correctly relative to the tank's center of gravity, creating a combination that could be flown controllably. This required detailed analysis of the specific tank's weight distribution and careful design of the wing attachment points and tail configuration. Baines addressed these challenges through careful aerodynamic analysis and, critically, by proposing a scaled test program before full-size development was committed. The 1/3 scale model that became known as the Baines Bat was designed to test the aerodynamic principles of attaching glider surfaces to a tank-shaped object, using a precisely scaled replica of the tank plus wing configuration that would gather data on stability, control, and handling before any full-size hardware was built. This was sound engineering practice, recognizing that the aerodynamic behavior of the combination might produce surprises that were better discovered at model scale than with a full-size vehicle and human crew. The 1/3 scale model was designed to be towed to altitude by a light aircraft, released and flown to landing by a pilot in the model itself, providing actual flight data rather than just wind tunnel measurements. The Baines Bat was constructed with considerable care, reflecting the seriousness with which the concept was being taken by the Air Ministry and the military authorities who were funding the development. The model was built to precise scale, with the tank hull represented by a ballasted fuselage that reproduced the weight distribution and center of gravity of the full-size vehicle. The wings were designed for high lift performance at low speed, essential for the tank glider to achieve safe landing speeds without excessive runway requirements. The tail surfaces provided pitch and yaw control, and conventional aileron controls on the wings provided roll control. The entire assembly was fitted with full flight controls connected to a small cockpit, accommodating a test pilot who would fly the model through its test program. The testing of the Baines Bat model revealed aerodynamic characteristics that were both encouraging and concerning. The basic concept proved feasible. The model could be towed to altitude and released, and it demonstrated controlled flight and a manageable glide slope that suggested a full-size vehicle might achieve similar behavior. The handling characteristics were described by test pilots as unusual, but not uncontrollable, with the high inertia of the heavy fuselage creating sluggish response to control inputs that required anticipation and planning well ahead of maneuvers. The landing characteristics were perhaps the most critical data point, as a tank glider that landed at excessive speed or with poor directional control would be useless regardless of its flight performance. The landing tests of the Baines Bat model produced data that illustrated clearly the fundamental challenge of the flying tank concept. The combination of high wing loading, resulting from the dense tank hull producing much greater weight per unit of wing area than conventional aircraft, meant that landing speeds were significantly higher than those of conventional gliders. A conventional military glider of the period might land at 50 to 60 miles per hour, a speed that was manageable on a prepared landing strip and acceptable on a firm, reasonably flat field. The tank glider combination required landing speeds considerably higher than this, speeds at which the impact loads on the tank's suspension and running gear would be severe and the risk of structural damage to the vehicle significant. Furthermore, the tank's ground clearance was limited, and the wing and tail surfaces attached to it extended both above and to the sides, creating a configuration that was vulnerable to contact with obstacles during approach and landing. The jettisoning of the wing and tail surfaces after landing raised its own set of engineering problems. The attachment points between the flying surfaces and the tank had to be strong enough to withstand the aerodynamic loads during flight, which at high angles of attack and in turbulent conditions could be very substantial. Yet these same connections had to be capable of being released quickly and reliably by the tank crew after landing, without specialized equipment and underfield conditions where speed and simplicity were essential. Designing connections that were simultaneously structurally robust for flight and easily releasable after landing was a genuine engineering dilemma, and the solutions proposed involved compromises that satisfied neither requirement fully. The weight penalty imposed by the wing and tail assembly was another significant practical problem. The flying surfaces needed to generate the lift required to carry the tank had to be of substantial size, and size meant weight. Every pound of wing and tail structure was a pound that reduced the tank's combat effectiveness, either directly by adding to the overall weight that the towing aircraft had to lift, or indirectly by reducing the fuel, ammunition, and supplies that could be carried in addition to the tank itself. Analysis of the weight budget for a full-size tank glider based on the Baines-Batt principles showed that the flying surfaces would add several tons to the total weight, requiring either a very powerful towing aircraft or a reduction in the tank's own combat weight that would compromise its fighting capability. The towing aircraft requirement was itself a major constraint on the concept's practicality. The Hamilcar glider, carrying a Tetrarch tank inside its fuselage, required a 4-engine bomber to tow it to operational altitude and speed. A flying tank, which would be aerodynamically less efficient than the Hamilcar due to its non-optimal shape, might require even more powerful towing to achieve usable performance. The 4-engine bombers needed for this task were among the most valuable and scarce assets in the RAF's inventory, committed to the strategic bombing campaign against Germany, and not readily available for towing experimental tank gliders on speculative operations. The diversion of even a modest number of heavy bombers to flying tank operations would have imposed real costs on other strategic priorities. The strategic context in which the Baines-Batt and other flying tank experiments were being conducted also shaped their ultimate fate. The concept had been conceived in the early years of the war, when Allied forces were on the defensive or at best conducting limited offensive operations. In this context, the ability to deliver armoured forces by air to unexpected locations seemed to offer genuine strategic possibilities, perhaps enabling surprise attacks on Axis positions that could not be reached by conventional means. But as the war progressed and the strategic situation evolved, these possibilities became less relevant. Allied forces were increasingly going on the offensive with massive conventional superiority in armour, aircraft, and artillery. The logistical infrastructure to support large-scale ground operations was being built up systematically. The need for improvised air delivery of armour was diminishing as conventional means became available. The operational experience gained with the Hamilcar glider and the Tetrarch tank in actual airborne operations also provided a dose of reality about the practical challenges of air-delivered armour. Hamilcar gliders carrying Tetrarch tanks participated in the D-Day operations and in Operation Market Garden, providing the airborne forces with their only organic armoured capability. The results were instructive. Landing gliders carrying tanks required good airstrips or at least firm, flat ground clear of obstacles, conditions that were not always available in the operational areas where airborne forces were dropped. Several Hamilcar gliders were wrecked on landing, destroying their Tetrarch tanks. The surviving tanks were vulnerable to German anti-tank weapons and were too light to engage German medium or heavy tanks effectively. The operational value of the air-delivered Tetrarch was real but limited, and it demonstrated that even with the more conservative approach of carrying the tank inside a conventional glider, the problems of air delivery were severe. The parallel development in Britain of other specialised armoured vehicles, the Hobart's funnies that included the Churchill AVRE, the Sherman DD, the Crab flail tank and other purpose-modified vehicles, provided alternative solutions to the problem of getting armour into difficult situations. These vehicles did not fly, but they addressed specific tactical challenges with engineering solutions that proved reliable and effective in actual operations. The success of these conventional but specialised vehicles reduced the urgency of the flying tank program, demonstrating that clever engineering applied to existing tanks could solve many of the problems that flying tanks were meant to address, without requiring the enormous technical risks of actually making a tank fly. The German flying tank experiments, which were being pursued in parallel with British efforts, added another dimension to the story. The Germans had their own experimental flying tank project, the Fliegende Panzer, and like the British program, it consumed engineering effort and resources without producing an operational capability. German engineers encountered the same fundamental problems: the aerodynamic incompatibility of tank shapes with efficient flight, the weight penalties of flying surfaces, the landing speed problems, and the towing aircraft requirements. German aircraft design philosophy tended toward powered flight rather than gliders, but the power-to-weight ratios achievable with available engines were insufficient to make a powered flying tank viable. The Germans eventually reached the same conclusion as the British. The flying tank concept was technically feasible in a narrow sense, but operationally impractical given the constraints of the technology available. American experiments with flying tanks took yet another approach, one that reflected the American tendency toward large-scale technical solutions and the availability of manufacturing resources that Britain and Germany could not match. American engineers studied attaching very large helicopter-like rotor systems to tanks, a concept that anticipated the helicopter-borne tank operations that would become possible decades later with turbine engines of sufficient power-to-weight ratio. In the 1940s, the reciprocating engines available could not provide anywhere near the power needed to lift even a light tank with rotary wing systems, and the American experiments remained firmly in the theoretical domain. But the basic concept, arriving at the battlefield in an armoured vehicle delivered by rotary wing aircraft, would eventually be realised in the helicopter operations that characterised the Vietnam War and subsequent conflicts. The formal cancellation of the Baines-Bat flying tank program and the broader British flying tank experiments reflected a pragmatic assessment that the resources being consumed could be more productively directed elsewhere. The engineering problems were not insurmountable in absolute terms, but solving them would require years of development work and enormous resources that were needed for programs with more certain payoff. The operational requirement that flying tanks were designed to meet was being addressed through other means, both through the Hamilcar and conventional glider programs and through the development of ground forces with the logistics infrastructure to deliver conventional armour where it was needed. The flying tank had been a creative response to a real problem, but it was not the only response, and in the wartime competition for scarce development resources, it could not justify its continuation against more immediately practical alternatives. The legacy of the British flying tank experiments, including the Baines-Bat, is found not in any operational weapon system, but in the technical knowledge accumulated during the programme, and in the broader understanding it contributed to the relationship between armour and air power. The aerodynamic data gathered from the Baines-Bat tests was incorporated into subsequent research on heavy-lift aircraft design. The analysis of the weight distribution and centre of gravity challenges of tank-shaped loads contributed to the understanding of how very heavy, dense payloads behaved aerodynamically, knowledge that proved relevant to subsequent cargo aircraft and heavy-lift helicopter development. The operational analysis of the concept's limitations contributed to the development of doctrine about what kinds of forces could and could not be delivered by air, helping to shape the realistic boundaries of airborne operations in the post-war era. The concept itself never entirely died. The desire to deliver armoured forces by air, to bypass the geographic and logistical constraints that ground movement imposed, was too strategically compelling to be abandoned simply because the technology of the 1940s could not realise it. Post-war development of turbine engines dramatically changed the power-to-weight ratios available for aviation, eventually making it possible to lift vehicles of increasing weight by helicopter. Modern military helicopters can carry light armoured vehicles, and the combination of helicopter mobility with armoured firepower has become a standard element of modern military doctrine. The H-64 Apache helicopter gunship carrying anti-tank missiles and cannon is in some conceptual sense the realisation of the flying tank dream, providing armoured firepower from an aerial platform, though it is the armament rather than the armour itself that flies. The direct lineal descendant of the flying tank experiments, however, is the family of air-deployable armoured vehicles that modern airborne and air assault forces employ. Light armoured vehicles, infantry fighting vehicles, and even some main battle tanks in their lightest configurations can be delivered by military transport aircraft and heavy-lift helicopters to operational areas, providing ground forces with armoured capability that was unimaginable in the 1940s. The Bradley infantry fighting vehicle, the M113 armoured personnel carrier, and their equivalents in other armies have all been air-delivered in various operations since the Second World War, fulfilling the basic concept that the flying tank experiments were attempting to realise, if through different technical means. The Baines Bat itself, having completed its test program and contributed its data to the flying tank development files, was eventually scrapped like most experimental aircraft that do not proceed to production. No examples survived the war, and the physical evidence of the program exists only in photographs, engineering drawings, and the technical reports that document the test results. These documents, preserved in British aviation archives, provide a detailed record of a serious engineering effort to solve a genuinely difficult problem, and they reflect well on the engineers and pilots who pursued the concept with professional rigour, even as the aerodynamic and engineering challenges made the ultimate impracticality of the program increasingly apparent. Looking back at Britain's flying tank experiments from the perspective of 8 decades, what is most striking is not that the concept failed to reach operational deployment, but that it was pursued as seriously and as professionally as it was. The Baines Bat was not a crackpot scheme cobbled together in a garden shed, but a properly engineered aeronautical development program, designed by qualified engineers, tested by trained pilots, and evaluated against realistic operational requirements. The conclusion that the concept was impractical with available technology was reached through evidence rather than prejudice, through actual flight testing rather than armchair theorizing. This is the essence of good experimental engineering: pursue the concept rigorously, gather the data, and make decisions based on what the evidence shows rather than on hope or institutional investment in a particular outcome. The story of the flying tank is ultimately a story about the relationship between strategic vision and technical reality, about the gap between what military planners want and what engineers can provide with available technology. The vision was clear and strategically compelling: armour delivered by air, bypassing every obstacle and arriving at the decisive point before the enemy could react. The technical reality was that the weight, shape, and landing requirements of even the lightest practical tank were incompatible with the aerodynamic efficiency needed for safe, controllable flight with the power plants available in the 1940s. The gap between vision and reality was not unbridgeable in absolute terms, but bridging it would have required either a revolution in engine technology or a fundamental compromise in the tank's combat capability that would have defeated the purpose of the exercise. In that gap between vision and reality, British engineers built the Baines Bat, flew it, gathered their data, and concluded that the flying tank was a dream deferred rather than a dream realised. The deferral proved permanent, at least in the specific form they envisioned, but the vision itself was vindicated by the subsequent development of technology. Today, armoured forces do move by air, do arrive at unexpected places with speed that ground movement cannot match, and do provide the combination of shock and firepower that the flying tank concept sought to deliver. The engineers of the Baines Bat program would likely recognise their dream in the air assault operations of the modern battlefield, even if the specific technical form it took was one they could not have anticipated. They were right about the vision. They were simply working at a moment in history when the technology needed to realise it was not yet available, and in their professional recognition of this limitation lay the wisdom that ultimately brought their program to its appropriate and honourable conclusion.